Hi everyone, I'm Dr. Ryan Tully-Doyle, and I'll be the professor for Math 143, sections 11 and 13 this quarter. I'm going to be recording some videos to support what I imagine is going to be a kind of a chaotic couple of weeks because of COVID and testing and people being in and out of class. Normally when I make videos, I put a lot of time into the production. This quarter, we're going to have to put up with the fact that I'm going to be doing in-person lectures as well. So my video lectures won't be as refined maybe as some of the lectures I've done in previous quarters. But in 15 or 20-minute pieces, you'll be able to get onto these videos and use them as either review, or if you're out sick, you can use them to learn the material. And then if you have questions, you can contact me in the Slack channel or in Zoom office hours. So I'll be holding my office hours over Zoom for at least the first couple of weeks to make sure that everybody can come, even if they're not physically in the classroom. So we're going to be doing things a little bit differently than the typical calculus class. The way the syllabus is set up for Calculus 3, if you've looked at it on the math page, instead what we're going to do is we're going to start with chapter 11. And the reason I'm doing that is because I think sequences and series kind of belong in their own section of the class. And then the other chapters kind of fit together because they're all about doing calculus with different kinds of variables, whether polar coordinates, parametric functions, or possibly functions of more than one variable. So the other thing to notice about these videos is that I'm not going to have the ability to edit these, at least not with the sort of time that I usually put in to make them elegant. So there may be things like me throwing the pen or making mistakes. I will try to make them as short as possible and not let them drag. The syllabus is posted on the course page. I'll be going over it in class. I'll encourage people to look at that. If you have questions, please contact me. So to make sure that this video stays short, let's get started. So we're going to be doing some advanced ideas in calculus. The way these things move, the ideas of calculus move from calculus 1 and 2 into calculus 3, is calculus 1 and 2 deal with derivatives and integrals. And in calculus 3, you start seeing extensions of the ideas of calculus to other settings. The first thing is, how do we deal with functions that we want to do calculus on, but don't have obvious ways to attack them with derivatives and integrals? And the answer to that is going to be, we're going to take functions and we're going to represent them as series, power series. So power series is probably the most important idea in calculus as far as applications in the real world. Replacing complicated functions with polynomials so you can do calculus on them is an incredibly powerful idea. It shows up all over math and science, and that's going to be the focus of the first part of the course, is chapter 11. So let's get started. So first we need to know what a sequence is. So we're going to build two series from sequences. So a sequence is a list of numbers. And in a list of numbers, I mean, it's a list of numbers indexed by something. So we might have A1, A2, A3. This is a typical way of writing what a sequence is. The numbers down here are called the index. So these guys are the index numbers. And it's a list of numbers indexed by the positive integers. So more generally, a sequence AN has n in the positive integers. And there's a couple different ways to write down what a sequence is. You could be just going to be given a list of numbers and you're supposed to figure out the pattern from the list. You can be given a formula and then you can generate the list from the formula, or a sequence could be given to you in a recursive form. So we could have things like, if you have a formula, it's easy to make a sequence if you have a formula. If I tell you AN is equal to n over n plus 1, what I'm telling you is the nth term of the sequence is generated by plugging in n equals whatever the number you happen to have, and that gives you that element of the sequence. So for the sequence AN is equal to n over n plus 1, A1 is going to be equal to 1 over 1 plus 1, A2 is 2 over 2 plus 1, A3 is 3 over 3 plus 1, and so on. I got to be careful about not writing over the top of myself. So let me put myself on bottom. There we go. That's better. Okay, so other ways you might see a sequence written include, you might see this notation. We could write a sequence n over n plus 1, where n runs from 1 to infinity. That's another notation for the same sequence. We already wrote down an is equal to n over n plus 1. Or you actually might get the list written out as 1/2, 2/3, 3/4, and so on. All of these are the same. This is equal to this, and this is equal to that. They're all the same idea. Okay. Going the other direction is actually the hard and fun direction, which is when I give you a list and you have to go back to figure out what the formula that generated the list is. So you could generate a formula from a list. And this is about recognizing patterns that show up. So, for example, if I tell you I'm looking at the sequence 3 over 5, 4 over 25, 5 over 125, 6 over 625, and so on, and I say, find the formula that defines the sequence, this is a pattern finding exercise. So I might say, find a formula for the nth term, an. Okay. This is where the first place in this chapter where people start having to stretch a little bit, because recognizing patterns is actually not an easy thing to do. It's not a thing that there's some sort of technique that we can tell you. It's about trial and error. So to continue that exercise, remember we had the sequence 3/5, 4 25ths, 5 125ths, 6 625ths, and so on. The thing to notice here is that this is the n equals 1 term, this is the n equals 2 term, this is the n equals 3 term, this is the n equals 4 term, and so on. And what we're going to try to do is we're going to try to relate the n's, that is which term in the sequence we are, with the numbers that are in that position. So to make this even clearer, this is the term a1, this is a2, this is a3, this is a4. And what we want is we want a formula so that an is a function of n. An is equal to f of n for some function. Okay? So how can I do that? Well, I want to try to relate the index to the numbers I see in the sequence. So one thing I notice here is that 3 is 1 plus 2, and 4 is 2 plus 2, and 5 is 3 plus 2, and 6 is 4 plus 2. It looks like we're adding 1 each time. And the way that I can relate that to the indices is to write this as, well, 3 is 1 plus 2, 4 is 2 plus 2, 5 is 3 plus 2, 6 is 4 plus 2, and so on. And notice that comports exactly with what we're trying to do. I mean, this is the n equals 1 term, this is the n equals 2 term, this is the n equals 3 term, this is the n equals 4 term. And I have a 1, a 2, a 3, and a 4 in the formulas that are generating the numerators of this sequence. In the denominator, I just have to notice that those are powers of 5. That 5 is 5 to the first, and that 25 is 5 to the second, and 125 is 5 to the third, and 625 is 5 to the fourth, and so on. So assuming that the pattern continues, it looks like this sequence is generated by the formula an is equal to n plus 2 over 5 to the n. Now that's not a proof. That's just an assertion that we've made about if this pattern continues. But for the purposes of this class, that's good enough. We don't have to go any further than that with this. All right, so that's basically the first kind of exercise that you see, is generating sequences by writing down a sequence from a formula and then finding a formula for a sequence given a particular pattern. I should point out here that it's easy to fall into the idea that every sequence has an easy formula that generates it, and that's generally not true. And the best examples of sequences for which The best example of sequences for which that is not true are recursive sequences. So a recursive sequence is a sequence in which later terms are not generated by a formula, but they're generated by looking at some combination of earlier terms. And the most famous recursive sequence is called the Fibonacci sequence. So let's look at recursive sequences. So the Fibonacci sequence you get by starting with two ones, and then you get the next term by adding the two previous. So 1 plus 1 is 2, and 2 plus 1 is 3, and 2 plus 3 is 5, and 3 plus 5 is 8, and 5 and 8 is 13, and 8 and 13 is 21, and so on. So this is called the Fibonacci sequence. And this is an example of a sequence that does not have an obvious formula. At least an explicit formula where I can find some function f of n that tells me what the nth term has to be. So instead, it's generated like this. f1 is 1. The first Fibonacci number is 1. f2 is 1. The second Fibonacci number is 1. And then you get the rest of them by combining the previous two with addition. So this part right here is recursive because it refers to itself. The sequence refers to itself. So these are nice ways of generating sequences, but in practice, they're actually very difficult to work with because if I want to compute, say, the 1000th term, I can't do that because I have no n to plug in to do it. So there are methods for discovering formulas for these. I'll tell you that if you're curious that the general term here is something like 1 over root 5 times, what is it, 1 plus root 5 over 2 to the n minus 1 minus root 5 over 2 to the n. That's the actual explicit formula for the Fibonacci sequence. And so there's entire classes on methods for finding those. That particular derivation isn't so bad. If you want to see it, you just ask. It's interesting. But it's not in the scope of the course. Okay. So the next thing that we're going to want to address here is we have these lists of numbers. We've got sequences, which are lists of numbers. And we want to calculate if those sequences are going anywhere. So it's possible that sequences can approach some number as they go out to infinity, right? Or as the number of terms goes to infinity, the sequence could approach a number, which is the idea of a sequence having a limit. So we say that a sequence has a limit if there's a number L so that the terms of the sequence AN get as close as we want to L. For all indices that are bigger than some fixed point in the sequence. So what I mean here, you can sort of think of this if you've seen the epsilon delta version of continuity or the formal definition of a limit in an earlier class. The basic idea here is that if I say, oh, I need to know if I say a sequence must be within 1/100th of its limit, you should be able to find a point in the sequence where every term past that point is within 1/100th of the limit. That's identical to the definition in the case of functions. Okay. So as an example of a sequence that has a limit, you can think of something like 1 minus 1/2 to the n. So 1 minus 1/2 to the n looks like, well, if n is 1, we get 1/2. And if n is 2, well, now we're taking away a quarter. So we have 3/4. And if n is 3, well, now we're doing 1 minus an eighth. So we get 7/8, and so on. This sequence looks an awful lot like it's converging to 1. As we continue on down the sequence, the numbers in our sequence are getting closer and closer and closer to 1. And so if that happens to be true, then we would say that the limit as n goes to infinity of an, which in our particular case here is the limit as n goes to infinity of 1 minus 1/2 to the n is equal to 1. Now the same rules apply to sequences and their limits that applied to functions and their limits. We get the same combination where sums of sequences that have limits have the limit, which is the sum of the limits of the sequences, and so on. All the stuff you learned about limits still applies here, even though we're plugging in integers instead of real numbers. But that's part of the nice thing about working with sequences is that we get access to all of this limit type machinery that we built up in earlier classes, including Lhopitals Rule, which is going to turn out to be really important. So it's possible that sequences can run off to infinity, and we have to be careful about what we mean about convergent and divergent in this context. Some authors say that a sequence can tend to infinity and converge there. Stewart kind of goes back and forth on this, where sometimes he notices that it's possible for a sequence to have a limit of infinity. It's not clear if infinity is included in the definition of convergent or not when we're talking about sequences. Generally, his approach is to say that if something converges to infinity, then it is divergent. So what do I mean by convergent? I mean a sequence converges to L if the limit as n goes to infinity of an is equal to L. In that case, it converges. And just to be careful here, L is not infinity or minus infinity. Otherwise, sequence diverges. And a great deal of what we're going to be doing over the first part of the course here is testing whether sequences or the sequences that arise from series converge or diverge, which is essentially a computation of a limit. So here's one way to attack this. If the limit as n goes to infinity of an exists, then of course an converges. And if you have a formula for an, so if I tell you a formula for the nth term, then really what you're doing is you're looking at the limit as n goes to infinity of f of n, whatever the function is that defines the sequence. Okay, so what I mean here is that if you have a formula an is equal to f of n, some sort of generating function for the nth term, you just compute the limit. So let's take a look at some of those. So for example, compute the limit as n goes to infinity of, say, n over n plus 1 if it exists. So we've learned a bunch of techniques for working with limits like this in earlier parts of the course. You could use Lhopitals Rule on this if you want, although that's a little weird because these aren't continuous functions. So if we want to use Lhopitals Rule, there's another step we need to make first, right? Technically, we're taking a limit as n varies over integers. So instead, what I can do here is I can just use the typical divide everything by n. So if I divide the top and bottom of this fraction by n, I get the limit as n goes to infinity of 1 over 1 plus 1 over n. Integers, real numbers, it doesn't matter. If I have the denominator of a fraction tending off to infinity, then 1 over that is going to converge to 0. And so this whole thing converges to 1 over 1 plus 0, which is 1. So this is a convergent sequence. It shouldn't be that surprising if you actually write the terms down, right? 1/2, 2/3, 3/4, 4/5, and so on. That sequence sure looks like it's converging to 1. And a lot of times you want to have kind of a heuristic or a experimental approach to if you believe a sequence should converge or not. That sequence to me looks like it's converging because it's getting closer and closer and closer to 1. That can be deceptive, but at least for the case that we're working at right now, there is no deception here. Okay, so I went in believing the sequence converged to 1, and then I can use math to show that it does. So another thing I'd really like to be able to do is actually use Lhopitals Rule, which is a theorem about continuous functions. So if I had a sequence that was of the form, say does the sequence an is equal to the natural log of n over n converge? I'd love to be able to use Lhopitals Rule on the limit of the natural log of n over n. But I have to make the observation that if a sequence is defined in terms of a function on integers, then I can look instead at that same function defined on the real numbers. It's a technicality, but an important one to notice. So the limit as n goes to infinity of the natural log of n over n, technically that is not something I can use Lhopitals Rule on because n is an integer. But there's a theorem that says that if that limit exists, then it's equal to this limit. Where x is a real number. And that's something I could use Lhopitals Rule on. Remember that Lhopitals Rule says that when I'm computing a limit of an indeterminate form, then I can consider the same limit but with the ratio of the derivatives instead of the ratio of the original functions. So by Lhopitals Rule here, I could rewrite this as the limit as x goes to infinity of 1 over x over 1, which is 0. So since this limit exists, this limit exists. Now, this is not something you need to point out in your own calculations unless I expressly ask you to do so. But it's important from the mathematical standpoint that the justification for using Lhopitals Rule here on something defined on integers is that there's a theorem that says that you can do this replacement. Okay. And so this sequence converges. An example of a sequence that doesn't converge looks like this. So there's a sequence that never settles down. It doesn't converge because it goes -1, 1, -1, 1, -1, 1. If you think about it as a function that we can plot, it doesn't settle into any particular number. It's bounded. So by bounded, I mean it never goes above this, and it never goes below that, so it's bounded, it's trapped. But a trapped sequence doesn't necessarily have to converge to a single number. So because this never settles down on anything, because no matter how far out in the sequence we go, if you give me, say, I mean, there's an infinite number of copies of 1 and -1, so it never pulls down like where it's collecting into a single number. So this diverges. Really because it looks like two convergent sequences that are glued together. Okay. Now there are bounded sequences that do converge. So let me make a formal definition of what a bounded sequence is first. So we say an is bounded if there is a number m so that minus m is less than or equal to an, which is less than or equal to m for all n. So it's the same as the picture I just drew on the previous slide. You have an m and its reflection minus m, and no matter what the sequence does, as long as it stays between those two numbers forever, the sequence is called a bounded sequence. Okay, so bounded sequences are useful. They show up a lot in practice. Another structural idea that comes with sequences, monotonicity. So we say that an is monotone or monotonic if an is increasing or decreasing. And by increasing, we mean an plus 1 is greater than or equal to an for all n. So that is, the sequence continually goes up and up and up, or it stays the same. But the idea here is the sequence is increasing if it never goes down, right? As you move further on in the sequence, the terms are always either staying flat or they're going up. And a sequence is decreasing if the opposite relation holds. An plus 1 is less than or equal to an for all n. And the big observation about the combination of monotonic sequences and bounded sequences, so a sequence is bounded if it's trapped in a band. It's monotone if it either goes up forever, which doesn't mean it diverges because it could be going up together to a horizontal asymptote, or decreasing if it has both properties. If it is bounded and monotonic, then a sequence converges. This is a big theorem. A bounded monotonic sequence converges. Okay, that's like one of the most powerful theorems about sequences, is that once you know a sequence has a bound and you know that it's monotone, it must have a limit. It's got to go somewhere. And I mean, the way to think about that is if there's a bound and the sequence is increasing forever, then that bound, if there's a smallest bound, it has to sort of be asymptotic. It can't go above the line, but it has to keep going up. So it must be being crushed in by some sort of horizontal asymptote. So one of the trickier things that you might be asked to do is to show that a sequence is increasing or decreasing or neither. Those exercises tend to look like this. So you could be asked to show that, say, n over n squared plus 1 is increasing. This will come up in this section and in later sections when we're testing for convergence of series. So it's an important technique to master. So we are being asked to show that an plus 1 is greater than or equal to an for all n. And the way we do that is we just write down the formulas for an plus 1 and an, which means plugging directly into the n's as if it's a formula. So the formula for an plus 1 says take this and replace all of the n's with n plus 1's. So we get n plus 1 over n plus 1 squared plus 1. This will be true if and only if this statement is true. So an plus 1 will be greater than or equal to an if and only if the formula for an plus 1 is greater than or equal to the formula for n over n squared plus 1. And that will be true if and only if algebraic manipulations are true. So this will be true if and only if n plus 1 times n squared plus 1 is greater than or equal to n times n plus 1 squared plus 1 for all n. And then if you do the last manipulation here and you simplify everything and you, this was all supposed to be decreasing, by the way. Here you go, editing in real time. So let's make this decreasing. When you're done doing the algebra here, what you should end up with is something that looks like 1 is less than or equal to n squared plus n. And that's just a true inequality for all n greater than or equal to 1. This is just true. And since that's true for all n greater than or equal to 1, then that means that all the previous statements are true as well. This being true for all n means that was true for all n, which means this was true for all n, which means that was true for all n, and so therefore the sequence is a decreasing sequence. There's another approach to this which involves writing down the formula and computing derivatives, and then showing that the derivatives are positive. That's a more advanced technique. We'll talk about that when we get to some of the later sections when we're talking about series. But the basic idea here is you're just algebraically manipulating. And the reason that we need to be able to do that is there are tests for convergence that we're going to be using later on when we're talking about power series that require that we're dealing with increasing or decreasing sequences to apply. And this turns out to be a way to do that. All right, so that's basically the content of 11.1. This is what these little videos are going to look like. Sorry about the lack of editing. It's just going to be the way it is because I also have to teach. So if I have a chance to go back and edit out some of the ums and the coughs and whatnot, then I'll do that. But I will post the notes for this on the Canvas page. And this video will be posted to YouTube, as will all the rest of them. There should be one of these for every section that we cover. I would encourage you, if you are out of class and you've been ill, or you have to miss for any reason and you're learning from the video instead of from me in class, please drop into the Zoom office hours that I'm going to be holding, or get yourself in the Slack channel and ask me questions if you have them. This is going to start kind of slow out the gate, but it's going to get tricky pretty quick, I think, at least in my experience. And just like in Calculus 2, how there were a bunch of different methods of integration that you needed to master in order to do well in the class, here there's going to be a bunch of ideas related to sequences and series that aren't individually hard. It's just that there's going to be a lot of them. All right, so I'm looking forward to seeing you in person, and take care.